Hello, and welcome to Simplifying Vertical Fusion. I'm Chris Greggs, Global Sales Manager for Polypropylene at McElroy. When I was given the topic of vertical fusion for this presentation, I considered several different approaches I could take for delivering the material. I discussed the challenges and experiences from the field with several of you and realized that most of the issues were just a matter of uncertainty. We're seeing more and more newer users finding themselves in applications requiring vertical fusion skills. And there just wasn't enough complete and accurate information available to allow these people to tackle their jobs with confidence. And to be honest, even some of those with experience weren't equipped with completely accurate information and instead relied on instincts or around here knowledge. I considered a demonstration format, but there are just too many variables and key steps in the execution to make demos alone effective. So we decided to essentially write the book on vertical fusion, putting together a complete reference guide that would give you one place to go when faced with vertical fusion. Now, this presentation isn't intended for the novice or the weekend butt fuser. Success with vertical fusion requires a combination of both art and science. Science being the theory behind how pipe is fused, and art being how we accomplish this through preparation and training, by managing our site conditions, as well as manipulating the various machine components and controls. We're going to cover both the science and the art, and if we're successful, we'll be able to address the middle ground on this graphic, this area where science and art intersect, the area of wonder. We hope to remove the uncertainty, to demystify the misconceptions, and in doing so, we'll simplify and organize your approach to this complex yet manageable field operation. The topics we'll cover are a bit more advanced in nature. My goal is to first give you a good understanding or awareness of the intricacies of vertical fusion. Second, to provide you with the proper techniques to perform a high quality, repeatable vertical fusion. And finally, to leave you with a basis or the toolbox you need to plan a successful vertical operation and to prepare your technicians to successfully carry out the work. We'll remove the uncertainty or wonder along the way. Thankfully, this presentation is being recorded, so you can use it as a reference in your own project preparation and training efforts. As we go through the material, I would encourage you to jot down any questions you may have, but I wouldn't take a lot of time trying to note the details because you'll have access to this presentation for future reference. We're going to start with a discussion of the theory of fusion, and we'll break down the various components of what determines our gauge pressure settings. We'll then take that theory and flip it on end to learn how we apply it to the vertical application. Then we'll make a game plan. Who's going to do the work? What tools do we need? Which process will we need to follow? And how do we get that done? And we'll finish with the execution of the actual fusion process and highlight some of the key techniques involved. We'll wrap up with a review, and I'll provide you with a few resources that may be useful to you along the way. So let's get started. At its most basic level, the principle of heat fusion is to heat two pipe surfaces to a designated temperature, then fuse them together by the application of a specified force. As the joint cools, the original interfaces are gone, and the two pipes have become one monolithic pipe. When we go vertical, the same fusion theory or the same principles or science apply, but the variables and techniques required to accomplish this can be quite unique. Let's start with gauge pressure. In theory, Fusion gauge pressure is just a mathematical equation, right? The OD minus 1 wall thickness times 1 wall thickness times pi times the interfacial pressure divided by the total effective piston area plus drag equals gauge pressure. It's that easy. So let me break that formula down and explain the various components, because you're going to need to have a good understanding of these variables and where this information comes from when we go vertical. In today's world, most people can rely on McCalc to help them determine the proper gauge pressure setting. But if you understand the math behind these calculations, it will be a huge benefit to you in vertical. In red, we calculate the theoretical fusion force. This is basically the interfacial area times the interfacial pressure. You see that the OD minus 1 wall thickness times 1 wall thickness times pi calculates the interfacial area, or the amount of surface area on the end of the pipe to be joined. And for McCalc, this is determined by your pipe size and wall thickness inputs. And IFP is the interfacial pressure, or the amount of force required to fuse 1 square inch of pipe or fitting contact area. In McCalc, this is determined by the specification you select. In blue, the TEPA is the total effective piston area on the machine you're going to be using. And this determines the ratio of pressure input to force output. This is just basic hydraulics, and in McCalc, this is established by your machine selection input. So the red theoretical fusion force divided by the blue total effective piston area gives us the black theoretical fusion pressure, otherwise known as theoretical gauge pressure. In a perfect world with no resistance to carriage movement, this would be the gauge pressure required to create fusion. In McCalc, this is the value you get if you set your drag selection to 0. And finally, there's drag. This is the amount of force acting in the opposite direction of movement. Drag isn't a calculated value. It's measured on the fusion machine. Although we often refer to the machine process or the steps involved in accurately measuring drag as the, quote, drag calculation. Measured drag has to be compensated for or overcome to ensure that the proper heating and fusion pressure is delivered. So we can think of drag as a balancing act. For forces acting on the pipe in one direction, we need a balancing force to ensure that our pipe doesn't move into or away from the heater during the heating cycle, and for fusion to ensure that the theoretical fusion pressure is delivered to the joint area. And the greater the forces acting on the pipe, or the higher the drag, the greater care we should give to accurately measuring and verifying our drag value. And the higher the drag force is in relation to the theoretical fusion pressure, the lower the margin of error we have to work within. The risk in miscalculation here is that we either consume our available hydraulic pressure to overcome drag, and there isn't enough left to create fusion, or we provide too much hydraulic pressure and squeeze out all of the molten material. Does that make sense? An early indication that we have perhaps miscalculated drag would be if our pipe separates from the heater during the heat soak cycle, or if it moves into the heater, forming an excessive melt bead. Now, armed with all these basics, you're all masters of fusion pressure calculation. So let's kick it up a notch, because there are a few different scenarios for drag in the vertical. On the left, you can see we have the movable pipe below, or on the right, we have the movable pipe above. With a movable pipe below and a fixed pipe above, we have an otherwise conventional or a normal drag situation. We'll refer to this as positive drag. The pipe is trying to move away from the fusion area, so we need to balance that with a positive force toward the fusion area. Or we can have the movable pipe above with a fixed pipe below. In this scenario, we would have a negative drag situation. This makes it a little more interesting because we have a couple of different possibilities that can exist when dealing with negative drag, and we'll deal with each one differently. Let me explain negative drag in a little more detail. In this scenario, the weight of the top pipe will be pushing down on the carriage. This extra force has to be taken into account when setting pressures for vertical fusion. We'll need to determine the amount of hydraulic pressure required to counteract the force of this pipe pushing down. This will represent our heating or drag pressure and will prevent the carriage from moving either away from or moving toward the heater. Remember that balancing act we discussed earlier. This value will also be used to calculate our vertical fusion pressure. Remember that for conventional fusion pressure calculation, gauge pressure is equal to theoretical fusion pressure plus drag. But in a negative drag application, the gauge pressure calculation becomes theoretical fusion pressure minus drag. The difference that results in this subtraction equation can result in either a positive vertical fusion pressure, meaning that we'll use the force of the top pipe pushing down to supply a portion of the theoretical fusion pressure, but we'll add to that some additional hydraulic pressure in the carriage closed position towards the fusion to deliver the proper theoretical fusion pressure. Or it can result in a negative vertical fusion pressure, meaning that the force of the pipe pushing down exceeds the theoretical fusion pressure. So we have to act in the open direction away from the fusion at a hydraulic pressure that will balance the delivered pressure at the theoretical fusion pressure. Remember, we're combining art and science. So at this point, you should have some understanding of the science or the theory behind vertical fusion. So let's transition now to the art or the mechanics of how we manipulate the machine to pull this off safely and successfully. This is about the game plan and execution. Who's going to do it? What tools will they have to work with? And how do they accomplish the task at hand? The game plan. Who's going to do the work? You're going to need a really good two-person team. One operating the HPU, the other with their eyes and hands on the carriage, the heater and the facer. These two need to have really good communication and a clear line of sight from one to the other. They both need to fully understand the theory. They should have the experience. And even if it's just in simulation or on a vertical stand. And they should have had the opportunity to practice their skills and demonstrate their proficiency. With this and the right tools for the job, they should have the confidence to succeed. As far as the tools go, smaller is better, lighter is better. You'll need good, clean serrations in the jaws or inserts to prevent slippage. The machine should be able to safely hold the jaws in the open position without depending solely on a hydraulic accumulator. It should give you the ability to measure and preset multiple pressures because you'll see we're going to need them all. And it needs to have the ability to both measure and control pressure on the carriage open and the carriage closed operations. Not just locked in position, but measure and control pressure in both directions. And ideally, it should give you the ability to load the heater and facer from the top or bottom of the carriage to provide you maximum flexibility in confined spaces. Now, what I've just described for you is a McElroy fusion machine. If you understand the challenges with vertical fusion, you'll also realize that our tools have all of the attributes required. And I couldn't imagine going to the field with anything less. So before we get into the mechanics of vertical fusion, we need to first identify the type of vertical fusion we're dealing with, or determine the optimum type given the people, tools, and unique site conditions we have to work with. What do we want to do? What's ideal? What's possible? And how do we give ourselves every advantage? There are countless scenarios and obstacles to be considered. Think about adjacent walls or pipes, the distance between the carriage and the HPU, your footing, the routing of hoses and cables, allowance for pipe movement, or even the orientation of the HPU in relation to the carriage to provide a clear and logical relationship between the actions performed on the HPU, such as carriage opened or closed, and the actual movement on the carriage. Because in vertical, there's no longer a left or right open-close relationship. Instead, you're shifting a valve to the left or to the right and creating a carriage action either up or down. A valve shift in the wrong direction or a lapse in judgment can spell disaster. And we should also keep in mind that vertical fusion or negative drag situations don't necessarily have to be inside buildings or straight up and down. Think about installing a pipeline up a steep grade, or perhaps down an embankment into a waterway with moving currents acting on the pipe. Many of these same principles will still apply. First, let's review the key steps involved in vertical fusion with the movable pipe below. Let's start by installing the carriage. Movable pipe below is the simplest type of vertical fusion and one of the most similar to conventional fusion on level ground. There are 5 simple steps you can follow to make this job of loading the carriage much easier. We start with figure 1. The pipe ends together and the fixed jaws positioned on the upper fixed pipe. In figure 2, we close and clamp the fixed jaws at the proper face-off distance. Then in figure 3, we use the hydraulics on the machine to position the movable jaws at the proper face-off distance. In figure 4, we close and clamp the movable jaws. In figure 5, we open the carriage to prepare for face-off. Now, I'm not going to cover the details of the facing operation here, but as with any facing operation, you need to be sure you supply sufficient pressure to create a cut and not so much that you stall the facer. Now we're ready to set our hydraulic pressures. With the movable pipe below, the weight of the bottom pipe will be pulling down on the carriage. This extra force has to be taken into account for vertical fusion for both the heating and fusing operations. First, we'll measure drag and set heating pressure. Regardless of the type of hydraulic control system on your macro machine, to do this, we select the center heating pressure PR valve, then measure and set drag in the same way that you would on a horizontal fusion. Since everyone here should be familiar with this operation, I'm not going to illustrate it, but I will talk you through the basic steps. First, we open the carriage so the pipe ends are about 2 inches apart. Then select the center heating PR valve. Turn the heating PR knob counterclockwise to its lowest setting. Move the carriage directional control valve to the closed position. Turn the heating PR knob up until the carriage starts moving. Then back it off until the carriage just stops. Note this reading as measured gauge. Repeat these steps to confirm your heating or drag pressure setting. Note that this heating pressure will represent the same as drag pressure on a horizontal fusion. Setting drag pressure properly prevents the carriage from moving away from or moving towards the fusion, resulting in an improperly made fusion joint. Then we calculate our theoretical fusion pressure with 0 drag and add our actual measured drag to this number. We then shift the selector valve to the lower fusing pressure and set this valve to the sum of theoretical fusion pressure plus drag. Heating the pipe with the movable pipe below. There are 3 easy steps, one of which is unique to this particular scenario. I'll give them to you in an ABC order. A, verify that the pressure selector control is in the lower fusing position. B, close the carriage to bring the pipe ends in contact with the heater. Allow for bead up according to the appropriate joining standard. During the heating process, you want to make sure the heater stays perpendicular to the pipe by supporting the heater handle. C, now this one's in red, so it must be important. After proper bead up, it's time to enter the heat soak phase of the heating process. Move the pressure selector up to the middle heating position and leave the carriage directional control in the closed position. This operation C is unique to vertical fusion and specific to the movable pipe below operation. Make sure the pipe remains in contact with the heater throughout the entire heating process. If the pipe loses contact with the heater for any reason, abort the joint and start over. You can't adjust your way out of this during the process and expect a good joint. This would be an indication that you've miscalculated drag, which would also impact your fusion gauge pressure setting. Fusing the pipe with the movable pipe below. A, shift the carriage directional control to the neutral position. B, shift the pressure selector down to the fusing position. C, open the carriage just enough to remove the heater. Quickly remove the heater and inspect the pipe ends for the appropriate melt. D, quickly close the carriage and bring the pipe ends together under fusion pressure. This portion of the vertical fusion process with the movable pipe below is exactly the same as when doing conventional fusion on a horizontal site. In this instance, we would allow the joint to cool under pressure to the rough handling time, due to the pressure being exerted on the freshly fused joint from the weight of the pipe below. Now, let's turn this process upside down and walk through a scenario where the movable pipe is above. We start by loading the machine onto the pipe in a 5-step process. This is the same as before, except upside down. Step 1 starts with the pipe ends together and the fixed jaws positioned on the lower fixed pipe. Step 2, we close and clamp the fixed jaws at the proper face-off distance. Then we use the hydraulics on the machine to position the movable jaws at the face-off dimension in step 3. Step 4, we close and clamp the movable jaws. And step 5, we open the carriage to prepare for face-off. Again, I'm not going to outline the specifics for the facing operation. It is important to note that the weight of the top pipe will be pushing down on the carriage. This extra force has to be taken into account when setting pressures for vertical fusion, including facing. It may be necessary to actually face with the carriage directional control valve in the open position to prevent stalling the facer. Let's set heating or drag pressure with the movable pipe above. Step 1, close the carriage. Step 2, shift the pressure selector up to the heating or drag pressure. 3, adjust the heating pressure reducing knob to its lowest setting. 4, move the carriage directional control to the open position because we're going to measure the amount of pressure required to support or lift the pipe up. 5, now to measure drag, we adjust the heating pressure reducing knob until the carriage begins to move up. Then adjust the pressure down until the carriage just stops. Then adjust the pressure reducing knob down until the carriage moves down. Then adjust it back up until the carriage just stops. This gauge pressure value will be your measured drag. We always want to repeat steps 1 through 5 to verify or confirm the correct heating or drag pressure. The heating pressure will represent the same as drag pressure on a horizontal fusion. Note that setting the proper heating or drag pressure will prevent the carriage from moving away or moving toward the fusion joint, resulting in an improperly made joint. Next, we set facing pressure so we can open the carriage after heating. With the carriage control knob in the open position, turn the facing pressure reducing knob up until the carriage can lift the pipe quickly. Note that facing pressure will be higher than heating or drag pressure. We'll use this facer valve as that extra setting or extra gear, if you will, required to break the vacuum that forms between the heater and the molten pipe material during the heating cycle and allow us to lift the pipe up quickly so we can cleanly remove the heater. Set the fusion pressure. To calculate the vertical fusion pressure, we calculate the theoretical fusion pressure first using zero drag and subtract the heating pressure. The heating pressure must be subtracted or the weight of the pipe will apply too much force and squeeze out the melt. Set the fusion pressure to the absolute value of the calculation. With the movable pipe above, the vertical fusion pressure equals theoretical fusion pressure minus heating or drag pressure. Remember that the result in this subtraction equation can result in either a positive vertical fusion pressure or a negative vertical fusion pressure, depending on the amount of force the pipe is exerting downward in relation to the theoretical fusion pressure. Each requires a different shift sequence, and we'll address each one independently. Let's start with heating the pipe in a positive vertical fusion pressure scenario with 4 specific steps. A, verify that the selector valve is in the lower fusing position. B, close the carriage to bring the pipe ends in contact with the heater. Allow for bead up according to the appropriate standard recommendations. Ensure the heater stays perpendicular to the pipe by supporting the heater handle during the heating process. C, after the proper bead up, move the selector valve up to the middle. D, this one's in red, shift the carriage directional control to the open position. This is counterintuitive, but very important. This operation D is unique to vertical fusion and specific to the movable pipe above operation. Ensure that the pipe remains in contact with the heater throughout the entire heating process. If the pipe loses contact with the heater, abort the joint and start over. Fusing the pipe in a positive vertical fusion pressure scenario with 5 steps. After following the recommended heating procedure, A, shift the directional control to the neutral position. B, shift the selector valve up to the facing position. Remember that we've preset this value at a pressure high enough to break the vacuum and quickly lift the pipe after heating. C, open the carriage just enough to remove the heater. Quickly remove the heater, inspect the pipe ends for the appropriate melt. D, shift the selector valve down to the fusing position. And E, quickly close the carriage, bringing the pipe ends together under fusion pressure and allow the joint to cool under pressure according to your prescribed recommendations. Now, let's examine the same scenario, but this time with a negative vertical fusion pressure and see what changes. We'll start with heating the pipe. A, verify that the pressure selector is in the fusing position. B, close the carriage to bring the pipe ends in contact with the heater. C and D are in red. They're important. They're different. Let's pay attention to them. C, when the pipe ends contact the heater, immediately shift the carriage directional valve to the open position. Allow for beat up according to the appropriate joining recommendations. Ensure that the heater stays perpendicular to the pipe by supporting it during the heating process. Again, C ends with the directional valve in the open position. Then D, after the proper beat up, move the selector valve up to the middle heating position. Like always, ensure that the pipe remains in contact with the heater through the entire process. If the pipe loses contact with the heater, abort the joint. In this case, operations C and D are unique to vertical fusion and specific to the movable pipe above operation with negative vertical fusion pressure. And we'll finish by fusing the pipe in a negative vertical fusion pressure scenario. Again, 5 simple steps. After following the suggested heating process, A, we shift the carriage directional control to the neutral position. B, shift the selector valve up to the facing to provide us with enough power to break the vacuum and open the carriage. C, open the carriage just enough to remove the heater, quickly remove the heater and inspect the ends of the pipe for the appropriate melt. And D, shift the pressure selector down to fusing pressure. And finally, E requires a double shift. This is in red, or a 2-step process. We'll call them E1 and E2. The first one, step E1, will quickly close the carriage, bringing the pipe ends close together. Then we shift to step E2, shifting the carriage to the open position, which will deliver the fusion pressure required to achieve the appropriate theoretical fusion pressure at the joint. In this case, operations E is unique to vertical fusion and specific to the movable pipe above operation with negative vertical fusion pressure. I also need to point out here that during the E1, the carriage will move very quickly, so ensure that the pipe ends don't make contact while closing the carriage at this speed. Closing under that pressure would push the melt out of the fusion area. If this happens, cut out the fusion joint and repeat the steps to fuse the pipe. The carriage will close slowly and at the correct fusion pressure during E2. So for review, remember, successful vertical fusion requires a combination of both art and science. My goals were to first give you a good understanding of the intricacies of vertical fusion. Second, to provide you with the proper techniques. And third, to leave you with a basis or the tools to both plan a successful vertical operation and to prepare your technicians to successfully carry out this work. We discussed fusion theory in detail and broke down gauge pressure calculations to help you understand the variables in the equation. A key component of this was measured drag, which we learned could be a positive value or a negative value in the vertical. And when drag is negative, the result can give us either a positive vertical fusion pressure or, in some instances, a negative vertical fusion pressure. And we deal with each of these differently. We discussed game planning with considerations for the people, experience, and competence required. We reviewed the tool attributes that are necessary and the various scenarios for the types of vertical fusion with movable pipe above and below. And we finished with the ABC steps involved in each of these unique processes giving you the keys to successful execution. You now have the tools to success in vertical fusion. And I want to leave you with a few bonus tools that I found useful for challenging vertical applications. The McElroy Vertical Fusion training stand on the left gives you the ability to train or to practice vertical fusion in any orientation. The Acrobat selection tool can help ensure that you have sufficient hydraulic power available to do the work, including how much remaining pressure you'll have available to overcome drag or to lift pipe. The reference section of the Fusion catalog contains a pipe and fitting installation guide and key carriage dimensions to help you plan and ensure there's sufficient clearance to install and remove the machine for fusion. And finally, there's McCalc to help you determine gauge pressure. Remember to use 0 for the drag value to get a theoretical fusion pressure, then either add or subtract the actual measured drag depending on the type of fusion at hand.
Chris, a great job putting together a presentation on a pretty difficult subject. There were a lot of questions about, and really breaking that into smaller chunks that hopefully people can ingest and understand a little bit easier.
Well, we'll see, Jesse. You know, it is a complex topic, but it's, as I mentioned, it is manageable, and we're thankful to have you on here today. Those of you that don't know Jesse or had the opportunity to work with him on one of these challenging projects, he's a great resource, and I am blessed to have him on here with me today to tackle some of these questions that may come up.
You give me too much credit, but thank you. All right, let's go ahead and get our first question going.
Sure.
One that's been voted to the top of the list, and the first one is specific to how much pipe can we pull or how much pipe can we fuse vertically. The question is there any limitation to the length of pipe that can be fused vertically?
Yeah, well, that's a interesting question, and the considerations for how much pipe can you pull or how much drag can you overcome and have enough remaining hydraulic horsepower, if you will, left to create fusion. The same is true in horizontal fusion if you're pulling long strings of pipe as it is in the vertical. The difference being in a horizontal fusion situation, you're not necessarily dealing with the entire weight of the pipe. In a straight up and down vertical, you're dealing with the full load. The example being the difference between trying to push a chair across a floor versus trying to lift a chair off of the ground. It takes two different, you're dealing with two different dynamics there. We do have some tools available to you. One that comes to mind for me, and one that I've actually used for this purpose, is the Acrobat selection tool available on the public website. The great thing about that is it can tell you, help you calculate how much hydraulic force you're going to consume to create fusion on any given size and SDR combination with any particular, in this case, Acrobat HPU combination. And there's a little button you can switch, and it will actually display for you the amount of remaining force, which would translate into the amount of power available to do that extra work or overcome drag.
Yeah, very good point. You know, while we're on this topic, something that I thought about was, you know, you only have a certain amount of usable pressure with whatever HPU you're using. So that's the amount of pressure that you can pull that pipe with. But there could be a scenario where the weight of pipe above becomes too much as well, and kind of along the same lines. If the weight of the pipe above in that configuration becomes more than what that HPU can hold open, that would be your limitation in that configuration, right?
Right, right. It's going to be the same in either orientation. You've got to have the hydraulics there, which brings me to a point I wanted to cover and really I didn't address a lot, and that's excuse me, just in the initial setup or evaluating the job site, the particular challenges that you have to work with. I can't say enough about giving yourself every advantage in terms of your approach to the particular fusion scenario that you're trying to deal with, the space that you have to work within, your organization around that space, your planning and preparation. And it just seems, at least in my experience, even if you have the ability to visit the site beforehand, do an initial evaluation, when you revisit the site at the time that you're going to do the work, things change. It's a dynamic environment on construction sites. And what you thought you were going to be presented with may be different. And so you really have to be prepared for every possible scenario at the time that you're going to be making the joint. I've even approached projects where I thought I would have the movable pipe either above or below. And when I actually attach the carriage to the pipe, what I find is when I use the machine to try to manipulate the pipe open or close, the pipe that I thought was going to move isn't the one that moved. And so you're left trying to sort of shift gears or rethink your plan at the 11th hour.
Yeah, and you mentioned it at the very beginning of your presentation. This type of fusion is not for the novice fuser. This is something that you really want to have your best, most knowledgeable people doing, because they're going to have to adapt and shift on the fly. If they don't understand all the different dynamics that you have going on, you could paint yourself into a corner, so to speak. So very, very critical to have somebody who really gets it doing this.
Right, right.
Let's move on to our next one. And the next question, again, specific to a certain part of the process, it is, should the weight of a heater be considered during the heat soak?
Should the weight of the heater be considered? Well, in a vertical scenario, gravity is going to be acting on the heater. So it's not going to be neutrally buoyant, if you will. It's going to apply some downward force. In my experience, I have not tried to weigh the heater, calculate that difference, take that into consideration in my settings. I just know that there is going to be some minimal impact of the force of gravity acting on that heater in a downward direction. The result of that is going to be probably a slightly larger melt bead formation on that lower pipe, yet it should still be uniform and continuous and give me the appearance that I want. So I don't take it into consideration in terms of the calculations, but I do always want to, and I think I stated it several times, support that heater fully throughout the heating cycle. So I don't want to give the weight of, for example, the cord or the heater handle or any external force pulling it in one direction or another.
I agree completely. You have a couple different things going on there. One being that lever that's being created by the heater handle. So supporting that and making sure that it's not putting uneven forces, on the lower and upper pipe during that process is important. The other thing that I've noticed, and this goes back to having somebody who really has some experience, understands what they're getting at, is that heater is putting some force, on the downside just because of gravity. And that is something that you may need to think about when you're looking at measuring drag and maybe trying to cheat just a little bit, especially on those higher heaters. You know, when you add that heater in on the downward movable side, that is now part of your drag calculation, but it can't be there while you're calculating drag. So
Right.
you may have to kind of do a little guesswork on, do a little practice, and it's something you'll just get a feel for over time, the more and more of these that you do.
Yeah, and you bring up a good point there, and you talked about kind of cheating on drag a little bit. It's not really cheating. It's giving yourself every advantage to win.
Yeah.
And the same can be true if you've got the pipe pulling away from the heater. If you're going to err on one side or another with drag, consider a little bit more to ensure that you don't get separation of those pipe ends from the heater during that heating process. It's, the difference between having enough pressure to maintain carriage position or to maintain contact and just enough to not have that is very minimal.
Yeah, it's a very fine line that you're walking there.
Right.
And one thing, additionally, when you're doing any fusion, but particularly with a vertical, because of these extra weights and sort of weight and balance calculation that we have to do, it is extremely important when you actually go to fuse the pipe to inspect those pipe ends really well and make sure that you don't have any of those common, negative indications like a concave pipe end, that would indicate that we had something set up incorrectly when we were heating under pressure. So.
Right. And that's been my observation on these types of scenarios where people with very good intentions will take on something like this and have the confidence and think they're doing everything correctly, yet the result that they get at some point, the melt doesn't develop as they had expected. They perhaps do have a concave surface there indicating that they heated under pressure. They just, because they don't do it every day, they need to be very conscious of those little cues that can alert them to, hey, maybe something's wrong in my process. I should step back, reevaluate, reconfirm the steps that I need to take to do this properly, make sure that that is in fact what I'm doing, and then move forward again.
Yeah, the devil really is in the details when you're doing these vertical fusions, and there are a lot of factors to consider, and those factors tend to have a greater impact on the outcome when you turn everything up on end. So
yeah, the volume goes way up on vertical.
Yeah. So that kind of leads us into our next question a little bit,
Okay.
which is this question. I'll just read it. It says, "What is the most important factor to consider when setting up a vertical fusion?" That may be a tough one. It's kind of a general question. Let's see if we can tackle it.
Yeah, well, that is what's the most important for me personally. As I approach a vertical installation, I'm gonna again give myself every advantage that I can, but I'm going to think through the process before I ever do it. I'm going to rehearse the process before I ever put a hot heater in there. I'm going to have practice that communication between the guy on the carriage and the heater and the facer and the operator on the HPU, so that just like you were rehearsing for a play or practicing on a sports field, I will have done this repeatedly before I actually ever get to the live game, so that I have the confidence to move through the process in an organized way. I think confidence is the biggest thing. We've outlined the process for you here. You've got a playbook, and the key is going to be in the execution of that play. And I think the only way to gain that confidence is through practice.
Yeah,
Your
that's
thoughts?
probably a really good way to answer that. If I had to take a stab at it, I don't know if I'd come up with much different answer. It really does come back to having somebody who's trained and understands those different factors, because there's so much variability that every scenario is going to have a different most important thing. So pretty hard to pinpoint one.
Right.
This is a good question that's getting voted up to the top of the list here, and has to do with negative drag. And they're just asking, how do we set negative drag pressure? And also throws in some data logger here. What with a data logger?
Well, you deal with measured drag is just a number. And on a McElroy machine with negative drag, you would measure that. You're measuring how much pressure is required to actually lift the pipe or make it buoyant, make it neutral. Okay, where's that balance? Not so much pressure that the pipe forces the carriage closed, and not so much pressure in the open position that you're lifting the pipe. You want to find that neutral, if you will. And what was the second part of it? Is data
the
logger?
second part is when you throw the data logger in the mix. So I'll kind of out a little here that setting or measuring negative drag pressure, the steps, whether you're using a data logger or not, don't change. But what you wind up with, and negative drag pressure, we're saying the weight of the pipe above movable is more than the fusion pressure that we need to apply. And because of the way that a data logger is plumbed into the hydraulic system on any McElroy fusion machine, that is the one thing that data logger is not going to accurately pick up, because it measures pressure in the closed direction. So when we measure pressure in the open direction, the data logger is going to give you a pressure, but it's not going to be that pressure that's actually being applied to the fusion joints. That is the one sort of setback you run into as far as data logging these negative pressure, or these negative pressure vertical fusions.
And I don't want our listeners, our audience, to confuse negative drag with negative fusion pressure. So you can data log a vertical joint, and the data logger is a valuable tool. But when you get into that negative fusion pressure situation, then you're not going to have the same type of pressure graph that you're used to seeing. You can still log the joint, but the pressure graph's not going to give you the type of appearance that you would expect on a more conventional fusion.
Yeah, definitely. Still a critical thing. Anytime you're doing these vertical fusions, is the data logger will help you really dial in that process. Things like measuring drag, making sure that pressures are set as accurately as we can. The difference there being, when you go to review a joint report, that joint report is not going to look like you're used to seeing in what we say a positive drag scenario. So it's just going to require a deeper level of understanding of what's actually going on inside that hydraulic system when you look at that joint report.
Right.
How about this? We've got a question here. It says, could we use any McElroy butt fusion machine for vertical welding, or is that only specific to polypropylene machines?
You can use any McElroy machine. It's not specific to polypropylene world. It's not specific to Acrobats. Our McElroy's conventional fusion machines are very well equipped to take on vertical fusion or deal with either high drag or negative drag situation. And that's the beauty of that manifold block design and our hydraulic control system incorporated throughout our line of equipment, is it gives you the ability to measure and preset the hydraulic values that are going to be required through the process. And I mentioned even going back and resetting that facer valve to yet another pressure, giving you that extra gear that can be required to separate the molten material from the heater after the heating process in certain situations. So
yeah, you know, I would answer that, you know, any macro diffusion machine can be used vertically. You know, our traditional polyethylene machines are not going to be as easy. You know, they're bigger, heavier, they're bulkier for a different purpose. But if you've got the means, you can absolutely do vertical fusion with one of those. We're getting short on time, so I'm trying to speed up a little bit here. We got a couple more questions to try to get to. We'll maybe get one more in here. I think we'll move on to this question about safety. Is there anything we should address more specific to safety when it comes to a vertical fusion?
Yes, and I'm glad we have just a couple of minutes to get this in, because I did not address safety specifically, but anytime you're dealing in a vertical application, you need to observe all of the safety precautions that you normally would on a construction site. You need to take extra care to secure the pipe. If the pipe should slip, if there should be a mechanical failure, if something unanticipated happens, that pipe has the ability to move very quickly and with a lot of authority, and it isn't going to warn you. So you need to be extra cautious that the pipe could move. And if it does, you need to have a way, you need to have it secure. It needs to be free to move through the range of motion required for fusion, but it needs to be tethered in such a way, whether it's with straps or pipe clamps or whatever, that should you have some catastrophic unforeseen failure, the pipe's not going to free fall and until it hits something you don't want it to hit.
Yeah, definitely. And, you know, red taping off the area below where you're working, that may be on a different floor completely. Whoever's down there may not know that there's a hazard. So just making sure that area is clear of any people or equipment that might get damaged.
Yeah, I think as well as giving extra care, even in clearing shadings, you know, yeah, that space between the pipe ends, just stay out of it. Just don't even put yourself in that position.
All right. Well, great Q&A session here. If anybody's got any other questions that they haven't had a chance to ask or think of later, hit us up in the virtual booth. You know, you can always reach out to Macro University, mcu@macroy.com. You can reach out to Chris or I directly, and we'll get you the right place to get your questions answered. So we're out of time, unfortunately. So thank you all for joining us. Thank you, Chris. Great presentation.
Thanks, everyone. Appreciate it.
All right. See you this afternoon.